For this video, I'm going to talk through some of the topics that we have this week, starting with features, themes, and layers. Okay, features are things on the ground that we can represent within a GIS. Now, I say on the ground because that includes things like trees, castles, houses, any kind of building, any kind of transportation network, such as a road, a railway. A feature is the particular thing that's on the ground. So a castle, a tree, a state, a county, a city, those are individual features. And that's important to really have clear. So a feature would be Arcata, California, the room that you're in, the Pacific Ocean, the General Sherman tree, one of the biggest trees in the world, Elandolin Castle, one of my favorites, or your house. So each of those would be a feature. A theme is when we group features together. And so we might have a theme that is trees. Now notice I said trees and not forest, because a forest would be different. It's a different type of feature. Trees is probably going to be a data set that's points with individual trees together, as opposed to a polygon of a forest. So those are two different things. So the theme would be trees, houses, castles, oceans, rooms, states, cities, etc. Okay, separate from the individual feature. Now, we don't use theme too much, but it is still really important because it is foundational for the next one that we use all the time, which is layers. And a layer is what we load into a GIS, and typically it has one theme in each layer. So as an example from the USGS, you can see we've got some property boundaries, elevation, geographic names, hydrography layer, land cover. Each one of these would be a layer that has a specific theme in it. And notice we've got one down here called transportation. Now you could have transportation, or you could have roads, and then you could have separate from that railways and canals. Those could all be layers with different themes. So how you organize your layers into themes is really important. And we'll spend a lot of time pulling layers apart and putting layers together, changing that organization of them and what's in a theme. Here's some examples. So typically we talk about files. Shapefile of cities for California. Now remember, shapefile is not just one file, but we call it a shapefile. That's the official name. State boundaries for the United States, shapefile with coastlines, a raster with elevations for Humboldt County. That would be a layer we'd load in. It's also a theme, the elevations for Humboldt County. Raster with temperature values for North America, another layer that contains a theme. Okay, and here's some more information on that. Okay, data models. So inside of each layer, there's data represented, and we're going to focus primarily on the spatial data for the near future. And there's two basic types we call vector data and raster data. Now you won't see vector data too much because we tend to refer to the individual types of vector data, points, lines, and polygons. Raster data we'll talk about a lot. These are two very different types of data. Vector data you've worked with it for a long time. Drawings that you've done in your life are going to be actually vector data. So three different types of vector data. Points, which are just individual, infinitesimally small points on the earth with a coordinate, always having at least an X and a Y, sometimes a Z. Could be lat long, could be easting to northing. Polylines are lines that are strung together, so really line segments that are strung together. Esri calls them polylines. The open source community calls them line strings. And here we simply have coordinates that have been strung together with line segments in between them. And so with this we can represent roads, streams, other things. And then polygons, and polygon is simply a polyline that's been connected back on itself. And again, coordinates for values for each of the corners, sometimes referred to as vertices. Okay, they're points that have been connected and then making something that's enclosed. Now polygons can also have holes in them, so the name is kind of a misnomer. We'll talk about a shapefile of polygons, but it can actually have holes in it. If you had something like a lake, that had an island in it, you might have to have a hole for the island. So polygon is a little bit of a misname on it, but close enough. Raster data model. Here's a raster. Looks like a photograph, digital photo that you've taken, except in this case it has elevation values. A bit more on raster data. So when you go out with your digital camera or your cell phone, you take a picture, you are taking a raster image. And they look kind of like this. And if you zoom in and then keep zooming in and keep zooming in, eventually you'll find that your image that looks like this is really made up of a whole bunch of pixels or picture elements. And the word pixel is really important because that's what we call each of these little boxes. Okay. And what those boxes have in it are just numbers. Now this photo contains red, green, and blue mixed together. We'll talk about more of that later. But really there's just numbers in here. So you can represent other things. In fact, you can represent a whole bunch of different things with a raster. Elevations, temperature, precipitation, salinity are common. These are all floating point data typically, or continuous data. You can do categories like land cover, forest, rangeland, water, rock, soil type, dominant species, disease presence, huge variety of different ones. And here's an example to show that this is a elevation model for Humboldt County. So you can see where the bay is and the ocean. It's very flat and zeros basically. And then we have the Eel River Valley coming up here. Let's see, that would be the Mad. So that's probably, yeah, that's got to be the Klamath, and then the Trinity. And I've just taken a small section of it and blown it up, and then blown it up, and then blown it up. And you can see that these are individual pixels. And what they have in them are numbers. And that's all that's in a raster, is a grid of rows and columns of numbers. And you'll hear us talk about rows and columns. You'll hear us talk about pixels and how big the pixels are, or the resolution, also known as the cell size. Now we don't talk too much about cell size. Usually we talk about raster resolution, but it is important to remember that that's the size of each of the cells, or the size of each of the pixels. Okay. Now, here's an example of having 1 meter resolution, 10 meter resolution, and 30 meter resolution. So a lot of folks would look at this image at 1 meter, which we can get very high resolution data, even higher than 1 meter now, and go, wow, why would you ever use anything other than that? Well, the problem is this data set is 100 times larger than this one, which is 10 times larger than this one. So as you go up in resolution, you also go up in data size, processing time, time to transfer the data. The reason it goes up by 100 as we go from 1 meter to 10 is because it goes up in both directions. Same thing here as we go from 10 to 30. Okay, it goes up by a factor of 3 in each direction, or 9 total, so about 10. So that's the real trade-off that we have to manage. Same thing with your digital camera. If you take a really high resolution photo, it's going to be big, it's going to take a long time to upload. You may not need that. With vector data, we pretty much just use shapefiles. It's an industry standard. It was created by Esri. They released it. It's now an industry standard, very broadly supported, works great, and it's really nice to have one file format. That is not what we have with rasters. There's over 100 different raster file formats used in the GIS world. It's really annoying. There's 2 that are used very commonly. Within the Esri world, Imagine, or IMG, tends to work best. It's the best supported by the Esri products. TIFF is pretty well supported by Esri, and it's also the International Interchange Standard. So not everyone supports Imagine. I believe it is now released to the industry, but it was a proprietary format. TIFF was an open format that was created. And then there's a whole bunch of other ones. And these can be spatially referenced. In other words, you can put spatial data and have it referenced to the Earth. These are not. So you do want to avoid BMPs, pings, and GIFs. Pings are used heavily on the web, but it's not a geospatial format, so it's not going to work as well. Your images are going to end up lost on the Earth. And typically what we do with these, we get data in these and we immediately convert it to an IMG or a TIFF file and then work with those. Okay, where does data come from? Data comes from all over the place. The surface of the Earth was originally surveyed with equipment and folks that dress like this, I guess, Surveyors, they travel all over the United States and around the world for hundreds of years manually surveying the earth. And this is still where some of our data comes from. This is still where your property, if you buy a piece of property, it's going to have an original manual survey associated with it on the legal deed, probably, most likely. Pretty cool stuff, but it's got some issues. Then we have satellites and aerial photography like Landsat, which we now have over 30 years of Landsat data. It's an incredible data set. We literally have 2 pixels for every 30 meter squared area on the Earth for almost 30 years. There's a little bit of a gap because of a problem with the satellite, but other than that, amazing data set. Aerial photos, which we'll be working with, some 3-inch data. It's very cool for Arcata. And then, of course, you've already worked with GPSs. Now, where you get most of your data is off the internet, which is great. It's an amazing resource. There's tons of data out there, and a lot of it is really, really bad because anybody can just upload data to the internet and it could go bad. So we have to be careful about who we download data from and how we qualify it to make sure it's going to work for what we're going to use it for. All right, so this week we are going to be doing digitizing. And I'm leaving this video up, even though there's another video for how to do digitizing inside of ArcGIS Pro. This one's for ArcMap if you want to access it. And manual digitizing, what we'll be doing, and there are automated methods, but this is where you're literally going around on the inside your GIS and clicking to digitize. You've already done this in the Island Paradise one. There's 2 different types, heads up or on screen. That's what we will be doing. There's also hard copy. This is where you have a pad and you're using a stylus to do the digitizing, and you can do this with a printed map, and I actually recommend it if you have a printed map because it's actually going to be more accurate and it's going to go faster and be higher quality. If you're doing a lot of digitizing, you probably want to do it through hard copy digitizing or on a screen that allows you to click on the screen. Okay, but we're not going to be doing a ton, and I've never used one of the other ones. I've always gotten by with doing the on-screen or heads-up one. Now, scale is an issue, and I don't actually use the term scale a lot. It's a very important term because it's saying how large the items are on our map. But because of the way it's phrased, folks confuse it all the time. A large scale map, folks tend to think of as covering a large extent, but it's actually the opposite. On a large-scale map, the objects are larger, which means it's a smaller area that's being described. So here we can see houses, individual houses, streets, etc. On a smaller scale map, objects are smaller. Okay, so you can't see any houses here on this small scale map. So I really don't use those much because you get confused. I've seen them confused in actual published documents. I tend to use the extent of your map, so a small extent or a large extent map. And folks seem to be less confused about that. But it is important. You can set the scale, but most importantly, what you want to be doing is thinking about where you want to be zoomed in. Do you want to be out here, which is probably not going to work out well if you're trying to digitize Arcata, or do you want to be really zoomed in? And we tend to be pretty far zoomed in when we're digitizing. Now, there's a bunch of different types of errors associated with digitizing. The Bolstad book has more of them, and I recommend checking that out. The big ones that I run into is where you overshoot. So you go past where you needed to, you don't close a polygon, or you undershoot, you don't quite reach it, or you miss a vertex. So if this was an example of 4 pieces of property, we would want to have 4 polygons here. And if we didn't have a vertex here, we'd actually have something very different, right? We'd have 1 big polygon and then 2. This would just be bad, right? We actually need to go and digitize each one individually, okay? Now, when we do that, what we want to do is have snapping turned on, okay? And snapping will force this to snap over to here, so we won't have undershoots and overshoots. The missing vertex you're going to have to take care of by making sure you go around this one, and then go to the next one with snapping on, and the next one and the next one. And snapping will make sure that the vertices are exactly at the same point. Okay, so there's a lot of things that determine how good the digitizing is. The scale, which we talked about, or the extent that you're at when you're doing the digitizing. The precision, using a mouse on the screen, you can do pretty well if you're zoomed in far enough. And where you're at, how you feel, how tired you are. You don't want to spend 10 hours digitizing straight. You want to take breaks because you'll get tired. And then the other issue is, what do we want to digitize? In other words, here's the HSU athletic complex. Do they just want the buildings? Well, if they just wanted the buildings, that wouldn't take long, right? You just draw rectangles around the buildings. But do they want everything, right? There's all kinds of complexity inside our sports field, including signs and a bunch of small buildings, the baseball diamond, or outfields, got the diamond. What is it they want? And so that's really important to make sure you know ahead of time as to how much complexity, because you could do digitizing for a really long time and get very accurate, very complex digitizing, but it may not be needed. So very important to know the purpose of the data. And last but not least is metadata. So metadata is data or information really about data. So we have our spatial data, which can have aspatial data inside the attribute table. That's what we spend most of our time focusing on. However, there's key pieces of information that we really have to have with our data if we're going to be effective with it, especially if we get data from other folks. And if you go to hand off data to other people, there's things that need to be in there. For me, the top three things are the source of the data, where you got it from. That could be digitizing, or more often it's a URL. So link to the web page where you got it from. Contact for additional information. If you're digitizing, that would be you. And then the date of acquisition or digitizing. Now, Esri has a standard that I'll show you when in the lab that I recommend using. It's pretty good. But I also think these things are really important. So description of each of the attributes, how the data was collected, that can be in the description. What was the original purpose? Again, the description, and then the approximate uncertainty of the data. There's really complex standards available for metadata. FGDC is the Federal Geographic Data Committee who created the FGDC standard that became the ISO, or International Standards Organization standard. It's incredibly complicated. For a while, they tried to require everyone to do full FGDC data, which was impossible. So folks we're kind of missing a guideline for what's a good set of feasible metadata to have. I'll show you again Esri's system, and I like it for what they have for required metadata. So you can put in a lot more than what they require, but they have a system where you can see what's required in their templates as you're editing.